Alabama STEM Explorers is made possible by the generous support of Hudson Alpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Holly Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, Alabama Math, Science, and Technology Initiative.
Thanks for joining us on today's episode of Alabama STEM Explorers. And today, Anderson and I are going to be exploring the properties of gases. And we're going to take a look at some pretty cool phase changes. Hey, Anderson, tell me, what's the coldest or the coolest thing you can think of? And I'm not talking about myself. I know I am pretty cool.
A popsicle, snow. Oh, I know, dry ice and liquid nitrogen.
Yes, those are really cold.
Do you want to chill, Dr. Lanier?
You bet I do. We are coming to you from the STEM lab at Southern Research in Birmingham, Alabama, where the weather is hot, but the science is so cool. And Anderson, you're in luck. I've got some dry ice and liquid nitrogen right over there.
Really?
Let's go check it out.
What even is dry ice? How can ice be dry?
That's a great question, Anderson. So dry ice is really just frozen gas. It's frozen carbon dioxide. And you know a little bit about carbon dioxide, right?
Yeah, isn't that what we breathe out?
That's exactly right. And the cool thing about dry ice, and really where it gets its name from, is that dry ice never changes into a liquid at atmospheric pressure. It just goes straight from a solid to a gas. And you can sort of see that a little bit here, but you know what, Anderson? Why don't you do the following thing? Why don't you pick up some of these dry ice pellets and throw it into these cylinders?
Oh, okay.
And all this is just some water, and I added some food coloring to sort of make it pretty. And you could just, go to town, throw something in. There you go. And so this gives you a better idea of how much gas is really coming off. Because the thing about dry ice, you can't see carbon dioxide gas because it's invisible, right? But whenever you put it into the water, you can really see how much gas is coming off. This is pretty cool, isn't it?
Yeah.
So I'm just gonna move these right out of the way, and I've got another experiment that'll help show you this. So what I'm gonna do is I'm gonna hold this balloon open,
okay,
and you're gonna take some dry ice and you're just gonna stick it right inside the balloon. Yeah, they're pretty slippery, they'll get away from you. There you go, perfect. Good job. You can add a few more in there. Perfect, one more. Great job. Okay, so now what I'm gonna do is I'm just gonna take this balloon and I'm gonna tie it off. And what I want you to do, Anderson, is I want you to take this balloon and I want you to give it a good shake. Shake it as hard as you can.
Okay.
All right, and keep on going. Don't be shy. Perfect. So if this dry ice is really frozen gas, what should happen is our balloon should totally fill up with gas, right? It should fill up with just carbon dioxide. So take a little sneak peek.
Whoa.
Yeah, it's blowing up, right? That's so cool, and it's gonna continue to sublimate. Have you heard of sublimate before?
I don't think so.
So sublimate is just when a substance goes from a solid to a gas without going through the liquid state. Pretty cool, huh?
Yeah.
So you can keep on shaking, and that balloon is eventually gonna get really big. But hey, Anderson, you said that you thought of something that was even colder than dry ice, right?
Yeah.
Which was?
Liquid nitrogen.
Yes, I've got some right over here. Let's go get it.
Oh, okay.
So you thought that dry ice was cold. It's about negative 78 degrees Celsius. Liquid nitrogen is even colder. It's negative 196 degrees Celsius.
That's really cold.
Yeah, it's freezing or below freezing. And so what I have here, Anderson, is I have some beautiful flowers just for you. Take a look, see that they're real, give them a good smell. Don't they smell delicious? Yeah, okay, so what I want you to do, so the cool thing about liquid nitrogen, it's really kind of just like liquid air. So most of the air that we breathe is nitrogen, about 79% or so. And so when that air gets really cold, the nitrogen turns into liquid nitrogen. I mean, it doesn't get this cold anywhere, but that's what would happen. And so what I want you to do with the flowers is I want you to give them a good dunk inside the liquid nitrogen.
Okay.
Do you see that? Yeah, so whenever you put those flowers inside of the liquid nitrogen starts boiling. And the reason for that is because compared to the liquid nitrogen, these flowers are on fire. So just like how you put a pot of water on a stove and it starts to boil, that's exactly what's happening here. All right, you can stick them a little bit further in there. Yeah, we want to cook them really good. All right, so now pull them out. All right, and I will take this right here, and now what I want you to do is I want you to give it a good squeeze. Perfect, now just let it go.
Oh.
Yeah, it is really cold, so it has totally frozen these flowers, and that is why you never want to stick your hand in liquid nitrogen. Pretty self-explanatory, am I right?
Yeah.
All right, Anderson, so we saw what happens when you put the flowers inside the liquid nitrogen, but I have some balloons right here. What do you say we blow some up and give them a dunk?
Okay.
Let's do it. That's pretty good. Okay, so now we have our balloons blown up, and so first we've got to put on our gloves, right, because this is super cold. Safety first. And so, Anderson, tell me, what do you think is going to happen whenever I dunk the balloon inside of the liquid nitrogen?
I think it might explode.
Yeah, maybe. A lot of people think it's going to pop. Well, the cool thing about science and scientists is when we don't know the answer, we just do the experiment. Are you ready?
Yeah.
Let's do it. All right, here we go. Cover your ears. Is it popping?
No.
It's not popping. What's happening?
It looks like it's deflating.
It is deflating. It's shrinking. It's totally shrinking.
Wow.
And I will pull this balloon out so you can see it a little bit better. Check it out. There is no more air inside of the balloon. Where did it go?
In the air?
Do you think that there's a hole in the balloon?
Yes.
Yeah, maybe there's a hole. So what do you think is going to happen when I pull the balloon back out?
It'll cool off?
Maybe. Okay, maybe it'll pop there. Well, let's just do it. Let's check it out. Are you ready? All right, check it out. This beautiful cloud. Now, what's happening to the balloon?
It's blowing back up.
It is blowing back up. Holy cow, why does that happen? I'll tell you. Okay, well, so think about it. So, like, when gases get really, really cold, what do? They want to get really, really close together, right?
Right.
And then as gases warm up, they want to expand. And so when we put this balloon inside of the liquid nitrogen, those gas molecules were freezing. And so they're going to try to get as close together as possible. You pull it out, now they're hot, they want to expand, and the balloon blows back up. That was pretty cool, wasn't it?
Yeah.
All right, Anderson, so we saw the pink balloon, but I also have a clear balloon here. We're going to do the same thing. I'm going to stick it in the liquid nitrogen, and of course, it's going to deflate, right, just like before, but this time when I pull it out of the liquid nitrogen, I want you to look really, really closely at what is inside, and I want you to tell me what you see. All right, you ready? Look at the bottom of the balloon. What do you see?
Liquid?
That's a liquid. What do you think that could be?
Did you spit in it?
No, I didn't spit in there. You saw me blow it up. So if I didn't spit, what could it be? So think about it. What gases are in the air? Because it's got to be something that's in the air, right?
Right. Maybe water vapor?
Water vapor. That's a really good idea. But think about water vapor. So what happens to water when it gets really, really cold?
It freezes.
It freezes into ice, right? Which is a solid, but that was definitely a liquid. So could not be water vapor. What else is in the air?
Carbon dioxide.
Carbon dioxide, that's great, because when I blow it up, that's what I exhale. Great hypothesis. And I have just the experiment to test that out. Do you remember that green carbon dioxide balloon we blew up from the dry ice?
Yeah.
All right, go grab it. Okay, so if you remember this, I know it's totally inflated. So if you remember, the only gas that is inside this balloon is carbon dioxide, right? Because it went from the dry ice, which is solid CO2, to carbon dioxide. So let's give this a good dunk. And if that liquid inside of our clear balloon was really carbon dioxide, we should see a liquid inside this balloon too, right?
Right.
All right, so it is deflated. Now I'm going to pull it out, and I want you to tell me what you see. All right, do you see any liquid in there?
I don't think so.
No, there's no liquid. You know what? This is just dry ice. It is a sheet of dry ice. Here, check it out. You can feel it. Because what happens to carbon dioxide when it gets really, really cold?
It
turns into dry ice, right, exactly. So it's not carbon dioxide. And so the gases that are left, you have a little bit of argon, nitrogen, because nitrogen, that's about 79% of the air we breathe, and oxygen. And it turns out that the liquid inside of this balloon is a combination of liquid nitrogen and liquid oxygen. Pretty cool, huh?
Yeah.
Very cool.
Dr. Lanier, what is all this smoke?
That's a good question. So it's not really smoke, Anderson. It's more of a cloud. And you know what? I have the perfect experiment that can show you. We'll make a little miniature, pretty cool cloud. All right. So what I have here is I have a flask of hot water.
Okay.
All right. And what I want you to do, Anderson, is I want you to hold it really tight, just like that. All right. And we're going to point it like that. And what I'm going to do is I'm going to grab some of this liquid nitrogen and I'm going to pour it in. And we are going to make a cloud. Because what happens, here we go, we'll give it a good pour.
Whoa.
All right, there you go, perfect, and check it out. Look at this cloud, and you can kind of breathe it in. It really is just a cloud. Doesn't that feel nice? It's exfoliating. Yeah, it's very cool. So what's happening is that like when we, this liquid nitrogen is coming in contact with this water, the water vapors cool down and they condense, and that is what makes a cloud. Isn't this very cool?
So
and we can just do this all day long. We can just keep adding liquid nitrogen, and it's just gonna make a beautiful, beautiful cloud. How neat is this? All right, yes, this is a pretty cool cloud, but I say let's do this on an even bigger scale. What do you think?
Yeah.
All right, let's do it. All right, so you saw that small cloud that we created earlier, but we're gonna make an even bigger one. So what I have down here is I have a bucket of liquid nitrogen, and then I have some hot water. So what I'm gonna do is I'm just gonna dump the hot water inside of the liquid nitrogen, and it's gonna go boom, and we're gonna have an awesome cloud. Are you ready?
Yeah.
All right, safety first. Here we go. Can I get a 3, 2, 1? This is so cool.
This is awesome.
Yes. This is the best cloud we've ever done. How cool is that?
Oh.
This is awesome.
Ever since I can remember, I loved building things. I can remember being real young and building things with sticks or rocks or whatever I could find that I could build with. And then I later discovered Legos and discovered that you can take these little bricks and build whatever you wanted. And as I went to school and grew up and learned that there's actually something you can do that's related to that, and I discovered that through chemistry you can build molecules. And not only build molecules, but build molecules that could help people. And if you're a doctor or a lawyer or something else, you help one person at a time. But by being a medicinal chemist and by working here at Southern Research trying to solve the world's hardest problems, we can change the world by the molecules we make. And every day I get up and that's what I think about. I think, is today the day that I'm gonna make a molecule that'll change the world? Chemistry is one of those areas where there's lots of different things that you can do. But medicinal chemistry is just what suits me because I'm still able to create and I'm still able to build things that can help people. I've worked on several projects here at Southern Research, but the one that we're working on now that's really exciting is for cystic fibrosis. It's been a real challenge with this project because it's something that's not been done before. So these types of compounds have not been made yet that can help. There are drugs on the market, but the specific ones we're going after are really new. And hopefully we can discover something that can make their lives better. You know, the next 5 years, I just want to continue to grow, continue to become a better medicinal chemist, continue to be a better manager. I have several people under me now. I just want to learn every day. I would say follow your dreams. You know, if you grew up with a curiosity for science, don't let anybody change your mind. Don't think about money, don't think about this or prestige. Do what you love, go after what you love. Because in the end, you won't be sorry because you're doing something that you love and something that is part of you. And a job is a lot more than a job. It's a big part of your life. And if science is that, then go for it.
Thanks for watching today on Alabama STEM Explorers. I'm Cruz.
And I'm Keisha, and we're here at Southern Research in Birmingham, Alabama. For today's scientific investigation, we want to make sure that we practice safety. So we have our safety goggles, which we're gonna put on. Good job, Cruz. And we advise that you do not try this at home. You should be under the supervision of an adult who is your parent or a science teacher when conducting this investigation. So, Cruz, that candle smells good. Where did you get it from?
Actually, my mom bought it for me.
Oh.
Well, I wasn't really playing with fire. Just, I was putting this lid over it to see what would happen.
Okay.
And just like that.
So you were just trying to see?
You just go.
Oh,
it went out.
Yes. So before you put the lid on there was a flame in the candle.
Yes.
So there were things that helped that flame to stay. So some of the things we know that it needs is oxygen, it needs fuel, and enough heat to keep it going.
Yes.
All of those together are called the fire triangle. So when you put that lid on there, we were able to extinguish that flame. So let's look at this a little more in depth, just to get a better understanding of what is actually going on. So let's put our candle to the side. You can put that lid back on. And we're gonna start here, and we are going to do an investigation. So we have 2 graduated cylinders here. Bring them closer to you because you know they're glass. We don't want them to fall over and break. So what we're gonna first do, we have our measuring spoons, and they are 1 teaspoon each. So I want you to put 1 teaspoon of yeast into both graduated cylinders. And when you put your yeast in there, make sure you level it off, like we did before when we were doing some previous activities. And say, we'll put 1 teaspoon, and I'll just hold this so it doesn't move around. Great.
There you go.
All right, and let's put 1 teaspoon here. All right. Now we're gonna do, after you finish that, we put that lid back on, we're gonna do 1 teaspoon of baking soda, also known as sodium bicarbonate. So if you hear the scientific term being used in your classroom, you know that means baking soda. So here we are with our sodium bicarbonate, also known as baking soda. We're gonna put 1 teaspoon here. Good job.
Enough.
That's right, that's enough. And then we're going to put 1 teaspoon in this graduated cylinder. All right. And then what I want you to do, Cruz, is to take it and just kind of mix it around like that. It doesn't have to be like perfectly mixed, but just mix it around, and we'll put this baking soda over to the side. All right, great. So now we have hydrogen peroxide, and what do you have on the other side over there?
Vinegar.
Vinegar, yes. Sometimes you may see the word acetic acid. Okay, and so we're gonna look at what happens when we put these different liquids into our graduating cylinder, and then we're going to provide a flame source, and then we're gonna see what happens. All right, go ahead. Pour enough in there, but don't let it overflow. Just a generous amount. We don't have to measure it out. That's why we don't have any lines on this graduated cylinder. Okay, just pour. Pour. Don't be afraid to pour. Okay, you can pour just a little bit more.
Okay.
Oh, yeah. And that should be good. Okay, and now here we're gonna pour hydrogen peroxide, also known as H2O2, into here. All right, just pour a generous amount. I think that is good. Now, as the adult, I'm going to light this little wooden popsicle. And we want to put everything out the way when we're working with fire. We want to make sure we have a clean work area. Now, this popsicle stick is going to be our fuel source. Okay, so we want to get this lit very well using our lighter that's providing this flame. Okay, I think this lit pretty good. What you think?
Yeah, that's really good.
So as the adult, I'm gonna drop that in here, watch. Oh. Did you see that? Let's see. Oh.
Whoa.
Did you see that flame come back?
Yeah.
Let's try this one more time. I think that was the last time. But what happened? Why were we able to extinguish the flame here, and then once I put the popsicle stick in here, the flame came back?
Because of the different liquids?
Well, it does deal with the components of what is in here. So what happened is we created a byproduct known as carbon dioxide when we use, what did we put in here?
Vinegar.
Yes, along with our baking soda and our yeast, right? So it created this byproduct, which allowed it to do what? What happened with the flame?
It extinguished.
It extinguished. But then when we put it back over here in the graduated cylinder that contains which different liquid? Hydrogen peroxide.
Hydrogen peroxide.
Good job. Yeah, we saw that the flame came back, but that was because we had O2 present, and that allowed that flame to reignite. So then we realized that, hey, we have to have certain components to make our flame continue or extinguish, correct?
Yes.
And so that's what happens when we're looking at flame and understanding how fire works. So that's why it's important not to play with fire. And that's why when oxygen continuously fuels the fire, which we got oxygen from the air that's in the atmosphere, that's what helps our fire to keep going.
My name is Tiffany Whitlow, and I am the co-founder and chief development officer at Acclinate. I am also the visionary of our now included community. Acclinate is a biotech company located here in Huntsville, Alabama, with a headquarters in Birmingham, Alabama. And we are working to ensure that there is diversity in clinical trials. Well, no day is the same because this is an uphill battle. And so people don't understand that when drugs are developed, like this albuterol here, this was developed through a process called clinical trials. In order to ensure that this works the same in me and maybe a white counterpart or my Asian friend, I need to make sure that there are enough people and a diverse representation in that research. And so that is really what we do. We meet people right where they are through our Now Included brand. We get to work with Johnson & Johnson. We have a location at J Labs in DC, and they're interested in getting feedback on Neutrogena and Clean and Clear and Band-Aids and Listerine. So who knew that these products that we used every single day were also developed through a process? And we need to make sure that people are engaged and included as that is being developed. Researchers are scientists, and they really some people maybe thought it was really cool and they were interested in their science experiments, but you can turn that into something that can help your mom or your dad with an illness. So if you have somebody that's suffering of a heart disease or diabetes, that drug that they're taking to help them with that disease state is developed by a scientist, by a researcher. You can be in the STEM field and not be a researcher. So if you failed that math test, if you're not necessarily good at that science experiment, you can still help those researchers. They need people who understand people and the lived experiences that we all go through. So it's really cool to think back of me as a middle schooler and what I didn't know at that time, that I could go into Walmart and get a pack of Band-Aids, but somebody had to figure out how that Band-Aid was going to go on your skin, how long it was going to stick to your skin, whether or not it was going to come off with water. That's developed through a process, and we get to be a part of that process. We get to support the tremendous research that's going on at Hudson Alpha, at UAB. We work with UAB a lot. We support the Alabama Department of Public Health. It's really cool to think that somebody who grew up in small town Alabama can solve big world problems. And we do have a lot more life and world outside of our small community. I never knew that was possible, but now it is.
Hi, my name is Zena. I've always wondered, what is fire anyway?
Fire is just oxidation, sped up by intense heat. The flames of a fire are a collection of very hot, glowing gases, such as carbon dioxide, along with steam, rising from the burning material.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of Hudson Alpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.